So now that we know a little bit about current, a little bit about wires, let's talk about components of circuits. These are things that we put in a circuit to do something. So we could say that a circuit component refers to one or more electrical devices or their equivalents connected in a circuit. The current entering a component has the same value as the current leaving a component. So let's illustrate a typical circuit, and we'll go over these symbols shortly. This pair of unequal parallel lines corresponds to a battery, a source of potential difference. And let's say in our circuit we have a resistor and a light. And we'll just go ahead and put an ammeter. An ammeter is a device that measures the current at a point in a circuit. So here's a basic circuit diagram. Now let's look at our resistor component. So this piece up here we call a resistor, this component. So a resistor, if you were to see a picture of a resistor that you can put in a circuit, they look like these little tubes in a circuit. And they are designed to restrict current flow in a certain amount, by a certain amount. Well, the thing is, current flowing through this component has the same value on the left end of this component, which we'll call point A, as it does on the right end of the component, which we'll call point B. The current entering a component has the same value as the current leaving the component. Well, let's look at a component that we could attach to a circuit. Maybe we attach a light. So I'll represent a light with just this loop and a circle around it. And we'll look on either ends of the light. So we'll look at a point on the left end of the light. We will just call this point A, and a point on the right end of the light, which we'll call point B. Let's look at the current flowing through this light. So the current will flow from point A through the light to point B. Now the thing about this current is, which I'll use the symbol capital I to represent a constant current. The thing about this current, if we were to measure the current at point A, and if we were to measure the current at point B, we would see that the current at point A is equal to the current at point B. So in other words, the current entering our component is the same as the current leaving our component. So it is good to realize and remember that the current entering a component always has the same value as the current leaving the component. Well, let's look at different components. So probably one of the most important, if not the singular most important component of a circuit is a source of EMF, something that maintains a potential difference in a circuit. So what you're probably used to are batteries. Batteries you might put in your flashlight, or you might put in another electrical device. So let's say I had two batteries. Now, a single battery in a circuit is represented by two unequal parallel lines. So this represents a cell in a battery, or a single battery for our purposes. If I attach these two batteries in series, basically connecting one right after the other, I would represent this combination with these two sets of parallel lines, where the battery on the left represents the first set and the battery on the right represents the second set. Now we could connect these two directly end to end. We could put a wire in between them, but when representing them in a circuit, we just put those two together just like this. And that represents our double battery system. If we could even add a third battery, and that would just be another set of unequal parallel lines. Now this battery maintains a potential difference in our circuit. So that means if we are to look at a single battery, the positive terminal maintains a certain value of potential at that point relative to the negative terminal. And that difference in potential will indicate as delta V is equal to the difference between the potential at the positive end and the potential at the negative end. And that's the purpose of the battery, to maintain that potential difference. Now, a capacitor is a device that allows us to store electric charge and therefore electric potential energy in a circuit. So typical capacitors you might see in an actual circuit are often cylindrical. And this cylindrical capacitor is typically two layers of conductors separated by a thin dielectric, so a thin insulating material. If you were to look at this from the top, this capacitor, that would be one conductor, another conductor separated by a thin insulating material, and this would be a cylindrical capacitor. And the thing about this cylindrical capacitor is it allows us to store charge between the two plates. So here is maybe the inner plate, this might be the outer plate, and let's say one plate has the higher potential than the other plate. And that higher potential plate has the positive charge, and the lower potential plate has the negative charge stored on it. And by establishing this separation of charge, this capacitor stores potential energy, which also means we have a difference in potential between the plates of a charged capacitor. Now, in our class, most of the capacitors we work with are parallel plate capacitors because they're simple to understand, simple to work with. And you might recall a parallel plate capacitor is just two parallel conducting planes that enable you to store charge. And we indicate these two planes in a circuit with just two parallel lines of equal length. One of these parallel lines corresponds to the plate that stores positive charge. The other parallel line corresponds to the plate that stores negative. Ooh, I think I said that backwards. Let's try it again. One of the parallel plates stores the negative charge. The opposite parallel plate stores the positive charge. And we indicate the capacitor as a component in a circuit, typically with two parallel lines. Now, a resistor is a device that is specifically designed to regulate the flow of current in a circuit. So if you were to look at a typical picture of a resistor or see a resistor in person, they would look like these little tiny cylindrical pills almost. And these resistors are designed to regulate the flow of current in a predictable way. Well, the quick way we'll represent a component that represents a resistor in a circuit is with this set of lines that look like a mountain range. Now look at how I drew this mountain range. It typically begins with a small peak, followed by a valley, followed by a mountain, followed by a valley, followed by a mountain, followed by a small valley, and that ends our resistor. Another component that we can put in a circuit is a voltmeter. The purpose of a voltmeter is to measure the potential difference between 2 points in a circuit. So a voltmeter, like you would have at home, a digital voltmeter would have a digital display. That digital display is designed to measure the potential difference between 2 points in a circuit. So let's say I attach this voltmeter up to a battery, a source of potential difference. And when I hook it up to the battery, I'm going to hook one lead up, typically called common, to the negative terminal of the battery, and I'll hook the other lead to the positive terminal of the battery. And what would occur here is this voltmeter would measure a difference of potential of positive 1.5 volts if this represented a battery pack that was equivalent to 1.5 volts across its terminals. Now, instead of drawing this whole big device, we just simply represent a voltmeter with a V and a circle around it. And when we put it in a circuit, we attach the voltmeter in such a way such that it is at opposite sides of a component, and that allows us to measure the difference in potential between both those sides of our component. So in other words, we can measure the voltage across a component by attaching a voltmeter on either end. Now, if we wanted to measure the current in a circuit, we would hook up an ammeter. The purpose of an ammeter is to measure the current through a single point in a circuit. We can measure the current coming into a component, or we can measure the current coming out of a component. The interesting thing is in the components that we'll be working with in this class, the current going into the component is exactly equal to the current coming out of the component. So how you would wire up an ammeter in a circuit, so let's say we want to measure the current moving through a resistor. So if we wanted to measure the current moving through a resistor, and let's hook this up to a battery. So here is, again, the long line represents the positive terminal of the battery. The short line represents the negative terminal of the battery. And let's say our circuit looks something like this. And I want to do something here. So I'm going to just do it like this. So our circuit isn't wired up yet. Now, if we want current to move through this circuit, we're going to want to create a complete closed path for that current to move, because once we have a complete closed path, the potential difference in our circuit will cause negative charges to go from low to high potential and positive charges to go from high to low potential. So if we wanted to know how much current is going through our resistor, well, we would hook the ammeter up either on one side of the resistor. This ammeter would measure the current going into our resistor, because remember, the current at all points in an ideal wire is the same. The current going into our ammeter is the same as the current going out of our ammeter, and that means that the current going out of our ammeter is the same as the current going into the resistor. Or we could also attach the ammeter on the opposite side of the resistor. And when we do that, we would see that the current leaving the resistor is the same as the current going through the ammeter. So the ammeter can measure the current coming into that component or leaving the component. And what it would measure is it would measure that the current into this resistor is equal to the current coming out of the resistor. And the last component that we have that we want to talk about right now at least is the ohmmeter. The purpose of the ohmmeter is to measure the resistance between 2 points in a circuit. Now the thing about an ohmmeter is you would attach it in such a way where its leads connect to 2 different points in your circuit, typically across the component you're interested in. So if we want to measure the resistance of that resistor, we would attach one lead of the ohmmeter on one side of the resistor, the other lead of the ohmmeter on the other side of the resistor. And in that way, we'd be able to measure the resistance of that resistor.